Hi everybody. We're going to be doing section 1.11, which is on some higher order differential equations. I know it's weird that chapter 1 is all about first order differential equations, but then at the last section, we're dealing with some higher order differential equations, and that's because we're going to be dealing with differential equations that can be turned into a first order differential equation using some tricks. So let's look at a second order differential equation. A second order differential equation looks like this. Second derivative dy dx, or second derivative of y with respect to x, is equal to some function of, remember you've got x's, you've got y's, and then you've also got dy dx's floating around. Okay? So what I should say is that certain second order differential equations can be solved using current methods after some clever strategies / substitutions. Okay, so we are going to study two different cases or types. So let's look at case 1. Let's talk about second order differential equations with the dependent variable missing. With the dependent variable missing. Okay, so what exactly does that become? So let me do this on the next page. This means that we have the second derivative of y with respect to x is equal to, you'll notice that the y is missing now. We only have a function of x and dy dx, right? There's no y's in there. This is just saying that there are no y's in your differential equation. What do you do when there's no y's? So here is our trick. The trick: substitute v equals dy dx. Okay? V equals dy dx. So here's what happens, okay? Our differential equation then actually is going to turn into, so star becomes 2 first order differential equations. So what do I mean by that? So what two differential equations does this become? Well, the first differential equation is, think about it, if v is equal to dy dx, then doesn't this mean that dv dx is equal to the second derivative of y with respect to x? All I did was I took the derivative with respect to x of both sides. So then one of the things that star becomes is as follows. dv dx is equal to f of x v. So that's a first order differential equation, isn't it? Okay, so this is our first differential equation. And then our second differential equation is literally the substitution. So dy dx is equal to v. Okay, let me give these names, okay? I will call this left guy differential equation 1, and I'll call this right guy differential equation 2. So what do you do now? You solve differential equation 1, and then you solve differential equation 2. You have to do it in that order because solving 1 finds v, and then plugging the solution into the second one is how you find, that helps you set up the second one, and then you can solve that. Okay, so let's do a quick example here. Let's solve the following. Second derivative of y with respect to x is equal to 1 over x times dy dx plus x squared cosine x, and x is positive. Now, right away you look at this and you say, oh wait, this is a second order differential equation, right? Because I see a second derivative, right? So this is a second order differential equation. So we know we can't use other methods, except you notice that there are no y's in this differential equation. You've got a dy dx and you've got an x squared cos x. So the dependent variable y is missing. Okay, this tells us to do the substitution, okay? So we're going to let v equal dy dx. And this means that the dv dx is equal to this. And so we end up with differential equation 1 is going to be dv dx is equal to 1 over x times v plus x squared cosine x, such that x is greater than 0. Okay? So, how do we solve this differential equation? Well, looking at this, you should hopefully notice that this is a first order linear, right? So we can actually get it in standard form, okay? So I'm going to subtract the 1 over x times v, and then this is going to equal x cosine x, right? This is standard form. Let me write this down too. This is first order linear. So we put it in standard form, and now we need an integrating factor. So I of x is going to equal e to the integral of negative 1 over x dx, which is e to the negative ln x, which is e to the ln of x to the negative 1, which is just x to the negative 1. You'll notice I did not need an absolute value of x because x was positive, right? That's given in the problem. So if I multiply everything by our integrating factor, which is x, I end up with, not x to the negative 1, right? I end up with x to the negative 1 dv dx minus x to the negative 2 v is equal to cosine x. Okay, what now? Remember, the left side can be rewritten as and the right side is just cosine of x. Okay, so now you integrate both sides. The left becomes vx to the negative 1, and the right side becomes sine of x plus C1. Remember, this is a second order differential equation, so we expect that we're going to get a second constant of integration later. And we will, because remember, we still have another differential equation to solve, okay? So I'm going to go ahead and multiply both sides here by x so we can get v by itself. And so we're done. V is equal to x sine x plus c1x. Now, what's differential equation 2? Remember, differential equation 2, remember our substitution was v is equal to dy dx. And so now we can just rewrite what we just got as dy dx is equal to x sine x plus c1x. So we just need to integrate both sides because this is separable, right? Doesn't this mean that dy, oh, well, even simpler, right? I mean, if dy dx is that, then we just need to integrate both sides, okay? So this means that y of x is equal to the integral of x sine x plus c1x dx. So this is equal to the integral of x sine x dx plus the integral of c1x dx. Why did I write it as two integrals? Because the left one we need to integrate by parts. Let me go ahead and work that out here. If u is x, then dv is equal to sine x dx. So that means du is dx. This means v is negative cosine x. And so this integration becomes uv, which is negative x cosine x, minus the integral of v du. We're going to minus a minus is plus, so plus sine x, right? And then what about this integral right here? This is going to be c1 over 2 x squared and then plus c2. And so we've got our answer. This is our solution. You could, if you wanted to, redefine c1 over 2 to be a new constant. You could call it like c3 or something, and then you wouldn't have to write c1 over 2, right? You wouldn't have a fraction at the end, but it's really not a big deal. Okay? So again, just as a recap, this substitution here, this is where we got our differential equation 2. And then differential equation 1 comes from making that substitution in the original. So we solved this guy, and then we put the solution in for v, and that's where differential equation 2 comes from. So this method is hopefully, it hopefully makes sense, this substitution. Let's talk about case number 2, because I mentioned that in this section we were going to learn 2 different techniques, okay? So case 2 is going to be second order differential equations with the independent variable missing. Okay, so in other words, we've got something that looks like this. Second derivative of y with respect to x notice now there are no x's, okay? X is missing. So what is the trick? The good news is the trick for this one is going to be the same as the trick for the other one. However, there is one little catch that makes these a little bit harder. So we're going to substitute v for dy dx again. Okay. Now, that's fine. The problem, though, is that where do we get the second derivative of y with respect to x? The problem is our differential equation has no x's in it. It only has y's. So we need to have only y's at the end of the problem, right? We can't have dy dx. We can't have dv dx, sorry, right? We need dv dy. So here's the trick then. The trick is to realize that if we were to look at this, this is the same as dv dx, right? But this is the same by the chain rule as dv dy times dy dx, right? Because v is a function of y and y is a function of x. But isn't dy dx equal to v? So if I replace it, I end up with v times dv dy, right? So we get v times dv dy. So this means that ultimately we're going to substitute v for dy dx, and we're going to substitute v dv dy for the second derivative, okay? So these are our two substitutions. We're going to do this substitution right here, and we're going to do this substitution right here. Okay? So what does our new differential equation become then? Star becomes, we have v dv dy is equal to f of y, and dy dx, remember, is v. So f of y v. Okay. So if we divide everything by v, we end up with, well, I should just say we should leave it like this and worry about solving this later, okay? This right here, I'm going to call this guy differential equation 1. What's differential equation 2? Again, it is this substitution that I made over here. So differential equation 2, remember, is this guy, v equals, this. Okay, so then you're going to solve differential equation 1 and then solve differential equation 2. Okay, so the steps are the same. The only new part is this right here, so I want you guys to be really careful about that. You need to have only y's in your problem in this one, right? So in the first case, you want to have only x's and v's. Here you want to have only y's and v's since the x's were missing. Okay, let's do an example for this one. I want us to solve the following. Second derivative with respect to x is equal to negative 2 over 1 minus y times dy dx squared. You will notice that this is a second order differential equation, and which variable's missing? The x is missing, right? So independent variable, which is x, is missing. Okay, so this is how we know that we're going to do this substitution. So I'm going to say let v equal dy dx, and then we know that dv sorry, wrong one. Second derivative of y with respect to x is equal to dv dx, which is equal to dv dy times v. And so we've got our substitution then. So star, let me go ahead and call this first guy star. Star becomes the following differential equation. We have v dv dy is equal to negative 2 over 1 minus y times v squared. What kind of differential equation is this? Okay, this looks separable to me, right? This is separable. Okay, separable. So we're going to separate the variables. We're going to divide the whole thing by v squared. Now be careful when you divide. So let me just say that if v is not 0, then we're allowed to divide by v, right? So if I divide by v squared on both sides, I end up with the following. 1 over v dv is equal to negative 2. You know what? Negative 2 over 1 minus y is the same as 2 over y minus 1, right? So let me just write it that way, and then dy. And then I'm going to integrate both sides. So what do we end up with? This gives us the natural log of v is equal to 2 natural log of y minus 1 plus c1, right? Let me just call it plus c1. So this is what we get. Okay. So what now? Well, what we can do is we can take e to the power of both sides. So this gives us absolute value of v is equal to, this is how I'm going to write it, e to the c1, and then e to the ln of y minus 1 squared, which is equal to e to the c1 times y minus 1 squared. We don't need absolute value anymore because it is being squared, right? So now what? To get rid of the absolute value, this actually means that v is equal to plus or minus e to the c1 times y minus 1 squared. But what I want to do is I just want to redefine a new constant here, okay? Why don't we give it a new name here? How about we call it d1, okay? So let's let d1 be plus or minus e to the c1. Which, by the way, you notice that can never be 0, right? It can never be 0 because it's either a positive number or a negative number. So let's remember that. This means that d1 is not 0, okay? So this gives us the following solution for the differential equation. I'm going to write it on the next page here. V is equal to d1 and then times y minus 1 squared. Okay, so now this brings us to differential equation 2. Remember, we had this, right? We knew that dy dx was v, and so that means we could take this guy and substitute it for this guy, and this leads us to differential equation 2, which would be dy dx is equal to d1 times y minus 1 squared. What does this mean? This is actually separable, but be careful, the y's have to go to the left, so I can write it this way. Y minus 1 to the negative 2 is going to equal d1x. So I'm going to write this with a dx, I'm going to write this guy with a dy, and then I can integrate both sides. How do you integrate the left side? That's just y minus 1 to the negative 1 over negative 1. So that's negative 1 over y minus 1. Okay, so we get negative 1 over y minus 1 is equal to d1 over 2 x squared plus, and then I could call this next constant d2, right? Or c2. Let me call it c2. So this is what we get. Okay. Now, can we solve for y here? Yes, we can. Okay. If we rearrange terms here, this means if we take the reciprocal of both sides, we end up with, and we can also multiply the right side by a negative. So there's a lot we could do here, but let me go ahead and multiply the negative through and also do the reciprocal. So this means that y minus 1 is equal to, let's see here, we've got, oh, I realize now that I made a mistake. I accidentally threw an extra x in here. This x shouldn't be there, right? So then this integral is wrong. So sorry about that. This becomes d1x plus c2, right? There is no square term because that was just an x. I think I did the integration in my head before I started. So, all right. So anyway, this is what we get here. And now let's go ahead and solve for y1. We actually get 1 over negative d1x minus c2, right? What I did was I multiplied the whole thing by negative. And then if I add 1 to everything, I get the following. Adding 1 means I'm adding negative d1x minus c2. And so you end up with the following. Okay. It's important to note here that d1 is not 0 and c2 is any real number, right? So this is our solution. Okay. Now, is that everything? There is one little thing that we overlooked, which when we came back here, remember we took the case of if v is not 0, right? I'm over here looking here. If v is not 0, then you get all this, right? But what about if v is 0? So note, if v is 0, then this means dy dx is 0, which means our original differential equation, if we take a second derivative, this means that the second derivative is also 0. And so our differential equation, look at the differential equation. Doesn't that become 0 equals 0? Zero equals 0, right? And so it works. Now, what does that mean? Well, this means that we get another solution if we look at this case separately. dy dx is equal to 0 means that y of x is just a constant function, c. Now, is any constant allowed? I want us to be really careful because in our original problem, do you notice that we have a 1 minus y on the bottom? This condition here means that y of x can't be 1. That's just not possible, right? That would not give us a solution to this differential equation. And so we end up with a whole other solution here, which is y of x is equal to c, where c is not 1. Okay, so this is the full solution here, guys. This and this make up the solution, the two things that I boxed. Thus, the general solution would be this box and this box, okay? So this covers every single case. So I want you guys to be careful. Anytime that you make an assumption, you divide by a variable, you're assuming that it's not zero, so you do need to go back and consider that case separately because it might lead to more solutions. You don't want to end up throwing away some potential solutions to your problem. Okay, guys, thanks so much for watching this video. I'll see you next time.